Hello everyone, I'm excited to welcome you to the online course Easy Geosteering. Here we simplify complex geosteering topics, breaking them down into easy to understand concepts. We are currently in the first part of the course, Necessary Theory, and in the previous video we found out what the target layer and formation deep are. And today we explore the structure map and offset wells, key components for building a geosteering model. Let's get started. Well, in the previous video we saw the target layer on the cross-section, its two-dimensional picture. But in real life, the top and bottom of the target are three-dimensional surfaces, and sometimes these surfaces have pretty complex shapes with local pits, hills, and slopes with varying depth. In geological modeling, we use the term structure map. It's a map showing the surface, shape, and behavior of a specific geological layer. A structure map is defined by strike lines and deep angles. A strike line is a line of equal TVDSS, and at every point it is perpendicular to the deep direction. A structure map or grid is an inextricable part of the 3D geological model of the oil field. The geosteering engineer receives it from the customer as initial input before support, in order to understand the layer behavior in the drilling area. So, to work with a 3D structure map in plan view, we need to transform it into a flat image. To do this, we use a rainbow palette to represent different TVDSS values. High TVDSS is shown in red and yellow, medium in green, and low in blue. Okay, now let's return to the example from the first video and analyze the structure map. The strike line spacing is 5 meters TVDSS, and the drilling pad is located on top of a local structural high. The slopes and local deep directions are toward azimuth 45 and 225 degrees. The current horizontal well is shown in black, and from the wellhead to point M1, it crosses only one strike line. But after that, we change azimuth and start crossing them almost perpendicularly, which means we are drilling close to the maximum deep direction in this area. We can also observe the structure map in the geosteering model. The current model is built in true hole length horizontal scale, which means we are making a cross-section along the well trajectory. The intersection line between the structure map and AA cross-section is shown in bright green. This line doesn't depend on the segment deep and remains constant while adjusting the model, unless we update the 3D structure map itself or change the well trajectory, since this line depends on the drilling azimuth. The structure map is a pre-job model, it may or may not match reality. To figure this out, in our example we need to compare the planned and actual T1 points. This is the initial planned trajectory, and its T1 lies at the intersection with the structure map. It has a TVDSS of minus 2148 meters, meaning a model mismatch of 12 meters from the real top target position. This particular value is quite large, but it can still vary either downward or upward, depending on the accuracy of a certain 3D model. Okay, now let's explore true and apparent deep definitions at a simplified example. Let's imagine we have structure map of the top target ideally dipping down from west to east at a constant deep angle of 4 degrees. And we have 3 horizontal wells. First one is planned in azimuth 0, second is planned in azimuth 45, and third is planned in azimuth 90 degrees. How do you think, what inclination should we have in each of 3 wells to drill inside the target? You can pause the video, think it through, and then come back to check your answers. Okay, let's see. The first well is planned with 0 azimuth, it means parallel to strike line. And according to definition of the strike line, if we make cross-section by line A, we will see no TVD changes of the top target. It will seem for us that the layer is subhorizontal. In this current example, with 0 azimuth, we have 0 apparent dip. The third well is planned parallel to deep direction. It means if the layer is dipping down with 4 degrees, we should have inclination of 86 degrees to drill inside the target. And here we have a definition. True dip is the dip angle in the cross-section perpendicular to the strike line. And only in this case apparent dip will be equal to true dip. And the last well, number 2. Here it might seem that we need to drill with inclination of 88 degrees as average between wells number 1 and 3, but it's not true. If we follow the correct way and use trigonometrical formulas in space, we will get fractional number 2.83 degrees for apparent dip. It means that we need to have inclination of 87-17 degrees. Okay, now we're getting to the next key term in the geosteering modeling, the offset well. It's neighboring well with geophysical data in certain target layer and above it. In the drilling process, offset wells are like references for us. We constantly compare the current well to offset, looking at logging readings, drilling conditions, and geology. And what is especially important, we create geosteering models based on offset well data. It's like a heart of our models. Here we have some requirements for the offset well. First of all, presence of logging, gamma ray is minimum. Since every horizontal well is drilled with at least gamma ray, we need to have gamma ray in the offset well to compare them with each other. And generally, the more logging curves offset well has, the better. The second point is good quality of logs. It's not enough to just have logging data. It needs to be of high quality without spikes and gaps. About logs quality and telemetry process we will speak in part number 2 of the course. The third point is the mutual proximity of the wells. The less distance, the better, because it reduces the chances of encountering unexpected geological conditions, such as fault or unpredictable layer dip. Generally, the best offset wells are pilot holes, vertical wells, and wells drilled parallel in the same azimuth. However, some wells from a neighboring pad drilled towards us may also work fine. And when we talk about the proximity, we mean the current bottom of the well, and during the drilling process, it's common practice to switch between offset wells as we go deeper. In our case, we can start with a pilot hole, then switch to a deviated well from pad number 2, and finally use vertical well number 3. The next requirement for the offset well, presence of direction and inclination data. Why do we need inclination and azimuth? To transform MD log into TVD. Why do we need drill floor elevation? To transform TVD into TVDSS. In one word, we need this data to build correlation scheme and geosteering model itself. And finally, when we plot the logging data in TVDSS scale, we need key geological markers to separate the main layers on the cross-section. This information, along with other offset well data, is provided by the customer before the geosteering support process begins. Alright, we have covered the structure map, the offset well, and the main requirements to it. Hope you like this video. Remember, you can take your geosteering skills to the next level with private lessons. Together we will work in StarSteer to apply all modern geosteering tools and drilling simulators to give you an experience of a true geosteering engineer. Stay tuned and give this video a thumbs up. In the next lesson, we will finally define the term geosteering and explore the 7 modern geosteering tools available today. See you then. Bye-bye.